Jim, you are the manager of Salt Creek Sanitary District here, and we're about to get a tour. Tell us what we're going to see.
Well, what we're going to see today is we're going to see the facility. We're going to talk a little bit about the history, and we're going to see our process systems. We have primary clarification, we have an aeration system, and a tertiary filter building that we're going to be taking a look at today.
Okay, let's get it started.
All right. First, what we have here is our preliminary and grit screenings room. This is where any rags or debris that would be in the collection system, sticks, twigs, rocks, this would all be removed. We have a bar screen system that would collect all the large debris. We collect it and deposit it in a hopper, and then we have a screening system which would catch all the fine grit, the road grit and small bits of gravel. It would wash out the organics from that, and the inorganic grit would go in our dumpster. We have two influent channels that come underneath this building, and the depth is about 16 feet.
Okay.
And so we have the bar screen that goes down there and pulls up the rags and debris, and then the grit washer pulls up stones and other debris and removes them from this process. Grit channel is our grit washer. It collects the grit from down below. It goes through an auger where it gets separated, and then the washed grit comes into the dumpster, and the rest of the water continues onto the plant to be treated. There, it would go over to we have a lift station that would pump to our primaries. After the flow goes through our preliminary screenings through the bar screen and the grit washer, the flow gets pumped to our primaries. And here at the primaries, what happens is the flow is slowed down, and the solids in the wastewater can settle to the bottom. And then when it settles to the bottom, we pump off. We have a flight and chain system, and we pump off the sludge.
How long does the water stay here to settle?
2-hour detention time in the primaries. During high flow events, that time will be less, but under normal design operation, about 2 hours, 2.5 hours. Chain on both sides of the tank. And what the flights do is they collect the sludge down to the hopper. We have a hopper at the bottom. And from this hopper, it gets transferred into our sludge pit. Here with the ear. Yeah. We're overlooking Salt Creek Sanitary District. We've just been looking at the primary collection system where we've been collecting sludge in our hopper to send over to the digesters. And what happens is we have a split here in the process. We're having an aerobic process, and then in the hopper area, sludge is being transferred to our anaerobic digesters. And the anaerobic digesters are the two tanks in the distant background, and that's where we have a digester that keeps the sludge at about 95 degrees to break down the sludge to reduce the pathogens in it. But right now we're going to focus on the aerobic part of the plant. And getting back to our pre-aeration basins here, we have one basin, the north basin here. This is the basin where our effluent from our belt press, after we dewater sludge, the highly concentrated filtrate comes into this tank. It's introduced with some bacteria from the activated sludge process, and then it gets treated and then released back into the plant. The tank that appears relatively empty, this is for storm events. When we have high flow rain events, the initial surge of rain and high flow, we fill up this tank, and then this reduces the impact of the high flow going through the rest of the plant. After the flow is treated through our primaries, where we have a reduction of about maybe 40% of the process of the treatment is done just by physically settling the suspended solids in the flow that are settled to the bottom of the tank.
Yeah.
The rest of the flow continues on to our activated sludge treatment system. Here is where we are introducing aerobic bacteria to the system, and there's an actual detention time of approximately 12 hours through our process here just in the activated sludge process system.
Okay.
We are taking bacteria that has settled out in our final tanks, which are the round circular tanks, and we are taking that settled bacteria and bringing it back to the beginning to pass number 1, which is this first aeration tank. That bacteria is being mixed with the effluent from the primaries, and what we have is our biological mass feeding on the food that is coming from our primaries, and this is the real heart of the wastewater treatment plant. What we do is we manage the food to mass ratio, or the amount of bacteria that we have available to the amount of food that's coming in.
Okay.
And if we provide the proper balance between the two systems, the plant will function ideally. The tanks with the aluminum railings has been a newer addition back in 2006. And what this has done is helped us to increase our ability to handle more flow and treat the flow that we do have better. It has increased our ability to stabilize and to settle sludge, so we can take as I said, we can take more flow and treat it better and have better settling characteristics.
Okay. Jim, you have a series of wildlife in here.
Oh yes, the ducks enjoy the water because at this point the water is pretty close to being about 90% treated. As far as biological treatment, that has already happened at this process. We are now, the mixed liquor or the activated sludge, if you look in the center column, is kind of a brown color, the same as the aeration tanks. Mm-hmm. But this tank settles all that activated sludge to the bottom, and then we have water going over the weirs. And from the water going over the weirs is going to go into our new filter building. But as you can see, we have plenty of ducks and birds, and we have a lot of wildlife here. And the water is, as I said, pretty close to 85–90% treated at this point. This is a round 75-foot diameter tank.
Okay.
There's a collector mechanism that goes around and collects and corrals the sludge to a draw-off tube in the center of the tank. And this draw-off tube is what gets pumped to aeration tank number 1 and completes the cycle of reintroducing the bacteria to the beginning of the aeration process. The collector system is constantly moving 24/7 all the time.
So these are, one's not backup and reserve, both are on hot.
They're both on all the time, yes. If we do have maintenance on one of them, we can drop one of the tanks down and perform the maintenance. The other tank does have the capacity to do about 7.5 million gallons if we need to on one tank. With both tanks, we can run at about 9.5 million gallons on a consistent basis. The effluent from the final tanks comes through underground. There's a lot of piping underneath everything around in the treatment plant, and right underneath the sidewalk is a pipeline that connects to the final clarifier effluent well. And what we have here is 3 pumps that are underneath here that pump the effluent from the final tanks to our new filter building. But before we go into our filter building, we're going to stop into the lab and take a look at the process and what we do in the laboratory. The control system for this one, we have a SCADA system that operates this plant 24/7, and it basically runs the plant and does the flow balancing and the monitoring of flow and alarms. In here we have the ability to see our flow rates from the final tanks, our return rates, the pumps that are running to return, and the pumps that are discharging to our filter building. We have various different We have the ability to look at our influent coming in and monitoring our sludge pumping that we saw earlier. We have 2 pumps that are pumping sludge from the primaries, and those are going over to the digesters, which are over here. In our upcoming improvements, we're going to be adding digester controls and new digester covers to our process, and we're going to be tying into the SCADA system, and this will help. It'll help coordinate and help us improve the running of the plant. In the laboratory here, we have a microscope that we use to look at the microorganisms that we have in the plant. We do this on a regular basis. We check the age. There's different types of microorganisms in their age, and what we try to do is have a medium aged sludge. One that's not too young, one that's not too old, one that's kind of like a teenager, kind of hungry and ready to eat all the food that's coming into the plant. So that's where we try to, we do our process controls for monitoring our solids inventory and the respiration rates on the microorganisms, and we do other tests throughout the day. This is our new filter building. It was just completed in January of this year. It's our Frederick Dale Tertiary Filter Building. We used to have a sand filter building, and the water used to get filtered through a sand filter, and then the water from there would go to our disinfection unit. Right now what we've done is we've put in a membrane filtration system. The filters filter a 10 micron down to 10 microns, and this leaves the water virtually almost solid free leaving the plant. The building is new and the filters are in operation. We're going to go inside and take a look and see how they're doing. We have four filters with a series of 15 discs in them. Right now we have each one of the filters is in operation. They're halfway full with water as a normal operating. Flow from the final tank that is pumped through the secondary control building comes to the building here. We have a bar screen, and this would catch any debris that may fall into the final tanks. Sometimes we collect branches from a windstorm or some other debris, and that's why we have a bar screen here to remove any large debris that might plug up or tear or the membrane filters. This is one of our filters. The flow comes in. It goes through the center of the disc. The flow goes through the membranes from the inside out and then transfers down to the effluent of the tank, and then it goes out to our UV system. We have 14 panels through the disc, and we have 15 disc units per filter system. Filter is a self-contained unit, so if we took one filter out of line, all the other filters would continue to operate. Each filter has its own backwash pump, a filter screening for the backwash, and it has its own effluent and influent valves. From the filter building, the flow is piped over to our UV disinfection system. And in the UV disinfection system, what happens is we use ultraviolet light to disinfect any of the microorganisms that could be harmful to, like the fecal coliforms that would be harmful to the stream or to humans. And so we use UV light. We used to use chlorine. UV light it doesn't leave any chemical residuals like chlorine does. And the UV light what it does is it neutralizes the bacteria or neuters the bacteria so they cannot reproduce, and therefore they won't be harmful in the environment. It's kind of bright out right now, but we have 2 banks to our UV system. There's 48 bulbs in each bank, and right now we're in relatively low flow, and we have 1 bank that is operating. Okay, the effluent from the UV, after the water gets treated to reduce the fecal coliforms, the water is discharged into Salt Creek. And if we take a look there, we can see we have some effluent that's currently leaving the plant right now. We're going to be looking at the anaerobic portion of the treatment plant. We've looked through to the aerobic portion earlier, but this is the anaerobic part, and this is where the sludge that is collected from the primaries is collected here, and it's pumped to our 2 digesters. And we're going to go take a look at digester number 1, and we're going to look at the operation of that. The sludge that comes from our primaries is pumped into our digesters. We have 2 digesters. We have one of them here is a primary digester, and then on the other side of the building we have a secondary digester. Our digestion time in our digesters is approximately 30 days. And what a digester does is it acts very much like a stomach. We keep the digesters warm at about 95 degrees, and the bacteria in the digester consumes the solids that are pumped over to the digester. And by the consumption of this bacteria, the sludge that is produced from a digested sludge is easier to dewater, and it doesn't have any vector attraction, or it doesn't have any nuisance bugs that are attracted to it, and it has a much lower odor than before it was digested. And it also reduces the pathogens in the process. So we're going to take a look at the heat exchanger and the gas compressor that mixes the digester in this building. We have a boiler. The boiler is currently, it is operating, but it's not fired up right now. It's maintaining the temperature of about 95 degrees. We have a heat exchanger. The brown pipes here represent this is the draw from the digester, comes into the boiler, it's through the heat exchanger. The blue pipes are actually the water jacket from the boiler bringing hot water into the sludge heat exchanger. And then the sludge is heated up to 95 degrees and then is returned back to the digester. And this is a continuous loop system to maintain the digester temperature. To help mix the digester, we have a gas compressor system. And the gas compressor system compresses the gas that's formed in the top of the digester, and it's used to mix the digester. The gas is recycled, and the gas compressor runs on a timer to keep the digested sludge mixed. And what that does is it not only just mixes the sludge, but when new sludge is introduced into the digester, it helps homogenize it, and so therefore it can break down more evenly and effectively. After the sludge is digested and it goes into our secondary digester where the supernate is decanted or sent off, the filterable solids are left in the tank, and the semi-clear liquid is sent back to the beginning of the plant to be further treated. The sludge comes to our belt press, and we have a 2-meter wide belt press that processes the sludge. Belt press is very much like a printing press. It basically has 2 belts that squeeze the sludge between the rollers, and we add a polymer to it to help dewater the sludge, to break the bond between the water and the sludge. The sludge is then processed between the rollers, is squeezed out, and then the deposited sludge is pumped into a hopper, and from the hopper it gets transferred to our dump truck, and then from there it goes out to the holding area. The digestion process, the sludge gets dewatered, and after it's dewatered, it's transferred into our dump trucks and brought out to our holding area. Now, if our belt press should break or something, or we need extra storage capacity, we do have drying beds that are available. However, the drying beds are not cost effective. The cost of the sand and the material and the labor to process sludge through the drying bed is cost prohibitive compared to running the belt press. The belt press is more efficient. For the same material dollars, we get 5 times the volume of sludge by running the belt press. And we have about 33,000 cubic feet of storage area here for sludge. And we hold sludge during the winter months when sludge cannot be applied to cropland. And that's usually from November 1st to about April 15th. And this is our sludge holding area. And as you can see, we're about a little over a quarter of the way full.